Welcome back, everyone. In this video, we'll be finishing up the section on definite integrals. So at this point, we know that if we are looking at a definite integral, we want to do a couple of things. First thing is it's representing an area, so that's very important. And when we want to evaluate a definite integral, at this point, all we can do is have the graph of our function. So for this first one, we would graph y equals 1 minus x. We would look at it from -3 to 4 and turn it in, look at it in terms of shapes that we know how to find the area of, which is pretty much on a graph going to be things related to circles, triangles, and rectangles. Pretty much nothing else is going to naturally pop up as far as a graph goes. So keep that in mind. Now, what I'm going to do is, because if I draw these things out and it won't be super perfect, I'm going to go ahead and just make sure that we look at the graphs actually drawn out well. So y equals 1 minus x. We only care about the x values from -3 to 4. So it might be a good idea if I do this, just kind of extend it out. So let's say from -4 to 5. So it goes out one further than we need it to. And then I'll just scroll in just a tiny bit here. So we got from -3 to 4, and we want to find the area. Now, because this is a straight line, this is not too bad to do. Could draw it by hand. Let's just actually scroll out a little bit. Actually, I don't like that. I want to keep the numbers there. So let me just pause it and I'll refresh when I'm ready. Okay, so this should look pretty good now. What we have is we have a straight line, but what we have to do is break it up into two parts, because we want to start at x is -3, which is right here, and go to x is 4. But we know when it's above the x-axis, the area is viewed as a positive number, or the integral, I mean. And when we're below the x-axis, so from x is 1 to x is 4, it's going to be a negative number. So what I encourage you to do is go ahead and think for a moment. When we're above the x-axis, what is the area here? It's a triangle, so we need the base and the height, and then do the same thing for the triangle over here from 1 to 4. It's below, so it's going to be a negative number, but what's the base and the height? And I'm going to go ahead and start setting it up just to write down, because now we know our shapes are two triangles. I'm going to go ahead and write down some information here. So triangle 1 and triangle 2. So triangle 2 will be the one below the x-axis. To find the area of these triangles, no matter which one we're looking at, it's 1/2 times the base times the height. So for triangle 1, the base, we're going from -3 all the way to 1. So -3 to 1, imagine boxing this in, -3 to 1, the x values increase by 4. So the base is 4, and the height goes up to the y value of 4 as well. So both the base and the height of triangle 1 is 4. Okay, so we've got 1/2 times base times height, but the base and height are both 4, so we got 1/2 times 4, which is 8. 16 over 2 is 8. And now what about triangle 2? Triangle 2 here, well, it's starting at 1 and going to 4, because we have to stop at 4. And the base is therefore 3. What is the height? Well, the height's going from 0 down to -3, so the height is also 3. The base is 3, the height is 3, they're both 3. So go ahead and write that down. So the area is 1/2 times the base times the height. But because it's below the x-axis, we know we're going to have a negative number. So it's -1/2, the base was 3, and the height was 3. 3 times 3 is 9, so this is -9 over 2. Now, based on the properties above, and really what we did in the very first problem, is we should add these two together. So the answer, our total integral here from -3 to 4, is the area of these two triangles added together. Taking account for the negative there, we have 8 plus -9 over 2. And if we multiply the 8 by 2 over 2 to get a common denominator, this is 16 minus 9, which is 7 over 2. And what happens here, even though we're not actually computing things, is you can actually type this into like a Wolfram Alpha or something and just check your answer. So you can actually use a lot of English here. So let's say we want to integrate. That's the word we use when we do an integral of something. Integrate the inside function, 1 minus x. And then I write from the lower x value, -3, to the upper x value, 4. Now, one thing to keep in mind here is when you're writing it in English, you don't have to use the dx because it understands x is from -3 to 4. So when you do that and hit enter, what you should see pop up is actually exactly what we're trying to do the integral of. And we see that it is 3.5. And actually gives you the nice visual representation. So we have the triangle above in one color, the triangle below in the other. Now the indefinite integral, that's something we haven't talked about yet, so do not worry about that. All right, now the next one here, this is actually kind of an important example because when you graph this, it looks like a circular shape. It will be a circular shape. And what happens is, without interpreting this as area, this is a really, really, really hard integral to do and takes a long time to actually do it based on just its formula. So pretty much anytime you have circular things, it's almost always better if you can recognize that's going to be a circular graph to just graph it and interpret the areas. All right, so what we got to do is we just have to do exactly what we did last time. We have no better option than to type it in and graph it. Okay, so we want y equals 2 plus the square root sqrt of 16 minus x raised to the 2 power. And now I'm just going to readjust. You'll notice that it only has this section here, and that's because the domain of this is from -4 to 4. If x is bigger than 4, then the square root becomes negative. So this is what the graph looks like. And we only care about from x is 0 to x is 4. So I'm going to go ahead and just adjust these settings. The x value, -4 to 0. The y value, well, we need to see it at 0, so this is fine. And I'll scroll out a little bit just so we can have a little extra room. And you see that y value goes up to 6. So let's just go ahead and move this up a little bit and we can see it better. All right, so the main thing you want to notice here is that the entire picture itself, this is a semicircle. Now I've thrown off really the scaling here because this is going from -4 to 4 and y value is already going to 20. So I'll scroll back in just so we can focus on our -4 to 0 x values. But the way you can know that this is actually a part of a circle, so y is the square root of 16 minus x squared, a part of a circle. Well, if you set it equal to the y and you square each side, let's go ahead and do that. Then you get y squared equals 16 minus x squared because it just knocks off the square root over there. And then you add the x squared to each side and you get x squared plus y squared equals 16. And this is the circle with radius. If you remember the radius, it's really r squared here. It's radius 4. So if I bring this back over here, what you'll notice is that our circle here, the x values that it goes from is -4 to 4. Half of that, so just from -4 to 0, the part we care about is actually a radius. Well, if this is half of a circle, then what we're doing is we're doing the area of the quarter of a circle. And what might help here is I'm going to actually draw this because we need to make sure we include the area all the way down to the x-axis, and I need to point out what is down here. So I'm going to go ahead and draw this. Keep in mind that at x is -4, we have 2. At x is 0, we have 6. And it has a semicircle shape. So I'm going to draw it on the side here. It's not important to draw it if you see the picture, but for the sake of this problem, I think it's more helpful. We got -4. The y value is 2. It starts there. And when we go up to x equals 0, the y value is 6. Well, what we want to do, what the integral wants us to find is the entire area down to the x-axis. We want to find this entire area A. I'll just write it a big A here. Well, we can break this down into two shapes, and hopefully you can see it. But if not, break it apart right here. Why? Because this down here in the bottom half is a rectangle. And this up here, this is half of a circle. So this is a 1/4 of a circle. Now, when it comes to circles, we know that the area of a circle, the only thing that matters is the radius, and we already pointed out this has radius 4. So this is 1/4 of a circle with r equal to 4. So when we find the area here, when we do the definite integral, we add these two areas together. The area of the quarter circle the area of a circle is pi r squared and r is 4, so it's pi times 4 squared, but because it's only 1/4, it's 1/4. And we can simplify this. 4 squared is 16 times 1/4 is 4, so this is 4 pi. Now that's not our entire answer because that's just the area of the quarter circle part. Now what is the area of the rectangle on the bottom? Well, that's just a rectangle, and the height is 2 because it goes from 0 to 2 on the y, and the width is 4 because the x values go from -4 to 0. So the area of the rectangle equals length times which is 4 times 2, and that is 8. And if we just add these areas together, we can't really combine them much, but that would be our total area. So, and that would represent the definite integral. So the answer here is 4 pi plus 8. Because once again, remember that the definite integral means the area with a positive sign, so we don't have to adjust it as long as it's above the x-axis. If this was all negative below the x-axis, we would have a negative on the whole thing. Right? But that is really the section. In the next section, what we'll finally do is relate the definite integral, which now we understand as area, and we can be a little more sophisticated about it because we can have negative numbers, but we'll relate the area to actually computing antiderivatives and how they're related. So I will see you there.